So, hello everyone who is watching on YouTube. Uh, since no one has joined the session in person yet, I'll wait for like 5-10 minutes before starting the session so that a few people can join it in person also. So, I'll get started in like 10 minutes, let's say. Okay, so I guess since no one has joined the session in person yet, we can just get started. So first of all, hello to everyone who's watching on YouTube. Once again, just to reintroduce myself, I am Lakshya, the discrete maths problem solving TA for the Monday 6 to 8 p.m. sessions. And in this session, we'll be discussing problems related to recurrences. So once again, I'll be assuming that you guys have gone through this week's lecture material so that you are comfortable with the problems being discussed. So yeah, I guess we can get started. I'll just share my screen and we can get started with discussing the problems. So yeah, let me just share my screen then. Okay, so I hope my screen is visible to everyone. So uh like uh like our usual sessions, I have some problems prepared for us. So there are 9 problems for today, and we'll be discussing these problems. Yeah, assuming that assuming that you guys know about the theory stuff which was discussed in the lectures, but still, maybe just for a recap, just sort of a revision, let's go over some of the basic definitions which were covered in the lecture. So this week was more focused on like knowing about recurrences and knowing about what is complexity. And so yeah, just revising, one thing to remember, how do we compare if a function f of n has a higher complexity than g of n? Because there are two functions given to us, then how do we say which of these functions has a higher complexity? So these are sort of two golden rules, I would say, while checking if f of n has higher complexity than g of n. So to check if a function f of n has higher complexity than a function g of n, we just need to check how f of n and g of n behave when n becomes very large. So when n tends to infinity, we need to check how f of n and g of n behave. And since n becomes very large, we tend to ignore the constant terms. We have to ignore the constant terms also. So for example, if even if we have something like f of n is equal to 50 times g of n, then still we ignore this constant term and we will say that f of n and g of n have actually the same complexity. So they don't have different complexities, but like if f of n is 50 times g of n, some constant times g of n, then they have the same complexity. And the high level intuition for this is this complexity part. Like when we say the function has higher complexity, we mean that this function has a higher order of growth than the other function. So one function grows much higher than the other function. But here you can see that if f of n is like something like 50 times g of n, then the growth of f of n is bounded by growth of g of n. Like if g of n grows by, let's say, 1, then f of n can only grow by 50. But if we have to find out if we have to talk about unbounded growth, then this is not a unbounded growth for f of n. 1 second, guys. I'll have to mute myself. Sorry. Hi. Sorry for that. So yeah, so as I was saying that if g of n grows by 1, then f of n can only grow by a constant which is 50 here. So it's not, f of n does not have unbounded growth with respect to g of n. And that's why we say like they have the same complexity. And like characterizing this in a more mathematical sense, we can say that f of n has a higher complexity than a function g of n if and only if, note that it's an if and only if, so it's a two-sided implication. So if and only if limit n tends to infinity, f of n by g of n is equal to infinity. So this function f of n by g of n, when n tends to infinity, if this becomes infinity, then we say that f of n has higher complexity. If this function becomes a constant, then we'll say that f of n and g of n have the same complexity. And if this becomes zero, suppose limit n tends to infinity, f of n by g of n becomes zero, then we can say that g of n by f of n actually becomes infinity. And that's why g of n in that case will have higher complexity than f of n. I hope it makes sense to everyone. I am not writing that down because I think it just follows, everything follows from this definition only. So yeah. Okay then. So I hope these two concepts are clear. Then we can proceed to uh, the questions now. So once again, starting questions will be more of easier questions so that we can get a bit comfortable with these concepts and questions. So yeah. So the first question states that which of the following are true with respect to growth of the function? So again, we are talking about so the growth means actually complex. Uh, so a function like complexity and growth of the complexity of function and growth of a function are two terms which are like sometimes uh, uh, used like in one can be used instead of another. So these two are equivalent terms in computer science. So like growth of a function and complexity of a function are terms which are used interchangeably. So this just means like which of the following is true with respect to complexities of the functions. So the first option, so maybe you can go option by option. The first option says that 500 n square is less than 1500 n. So note that we are only talking with respect to growth of the function. This is not an actual inequality. So don't think of it like okay, 500 n square is less than 1500 n. Then this denotes that n square is less than 3n, and so we get n is less than 3 or something like this. Note that we are not talking about actual inequalities here. These less than greater than signs are just for a reference, and they denote the complexity of the function. So this statement actually denotes that the function 500 n square has a has lower complexity than the function 1500 n. This is what we are talking about, that the function 1500 n square has a lower complexity, and so like 1500 n has a higher complexity than 500 n square. But note that this is actually false. And this is false because, uh, as I said, that we ignore the constant terms. So these 500 and 1500 can be ignored. And between n square and n square has a higher complexity than n. And this can easily be seen like just like this you must know already also from the lectures, but you can just see it by this limit definition also. Like if you put f of n as n square and g of n as n, then n square by n gives us n, and limit n tends to infinity of n is just infinity. That's why 5 and n square has a higher complexity than n. And so 500 n square will also have a higher complexity than 1500 n. So this statement is actually false. And why this false? This is because n square has higher complexity than n. Something like this. Similarly, coming to option B says 5000 n square is greater than n cube. Again, like don't think of it as an inequality and just say that 5000 is greater than n by canceling n square from both sides. This just means that instead what this means is that 5000 n square has a higher complexity than n cube. This statement denotes this claim that 5000 n square is greater than n cube. But note that again, this claim is also false because again, ignoring the constant 5000, we have that n square is greater than n cube. But n square does not have a higher complexity than n cube. N cube has a higher complexity than n square. So this is also false. False as n cube has Coming to option C, it says 300n is greater than 3n square. Again, ignoring the constants, this means that n has a higher complexity than n square, which is again false, as n square has higher complexity. Option D says 999n squared is less than 9n cubed. And this is true, ignoring the constant, because n squared has a higher complexity than n cubed. So true as so n squared has a lower complexity than n cubed, so n cubed has a higher complexity than n squared. Okay, then so only option D is true. So which are the following are true? We have to mark. So A, B, C are false, and only D is true. So hence option D is correct. Okay, pretty straightforward question. Now moving on to the next question. Second question states that how many n-bit binary strings are possible without having consecutive ones. So let's say T of n denotes the number of n-bit binary strings possible without having consecutive ones. Then we have to find out what is the correct recursive relation between what is the correct recursive relation of T of n. So there are different options given to us. So we'll not go option by option, but rather we'll try to derive the recursive function ourselves. So let's just get started maybe. So let T of n denote the number of n-bit binary strings without consecutive ones. The number of n-bit binary strings without consecutive ones or without having consecutive ones. So this is the number whose recursive relation we need to find, right? So it's easy to look at the base cases first of all. So in base case, suppose let's say we want to find the value of T of 1. So T of 1 just denotes the number of binary strings of length 1. So 1-bit binary strings, which do not have any consecutive ones. So it's easy to see that this will be just equal to 2 because T of 1 can be 0, T of 1 can be 1. And like, okay, not T of 1, but like the 1-bit binary string can be 0 as well as 1. In both the cases, there is no consecutive ones because there is only 1 bit anyways. So that's why both 0 and 1. So um, maybe I should mark the strings also, write the strings also. So this is the first string, the 0, and the second string will be just 1. Yeah. So both these strings do not have any consecutive ones and are length 1. Similarly, T of 2 will be equal to, so this will be 2-bit binary strings without consecutive ones. So note that 0, 1, 1, 0, and 0, 0. These three strings, so 0, 0, 0, 1, and 1, 0. So these are the three strings which won't have consecutive ones because the fourth string will be like there are only four possible 2-bit strings, right? Because 2 raised to power 2 is 4. But the fourth string 1, 1 will have consecutive ones. These two ones are consecutive. So this is not part, but these three strings are. So T of 2 is equal to 3. Okay, so we have the base cases covered, and now we can go to the recursive definition. How can we define this recursively? So for defining this recursively, what we can do is just denote the n-bit string like let A1, A2, A1, A2, A3, then AN be the n-bit string which we are looking for, and this is the n-bit binary string, and here we have that all AIs are 0 or 1. Then Now we have to look at different possible cases for these AIs, right? This is the n-bit binary string which is given to us. All AIs are 0, 1. So now let's look at the different possible cases for this A1 first. Like, uh, let us look at the, okay, let us look at different, or maybe let us look at the first bit, which is A1 of the n bits. Then there will be there will be two cases. So case one will be like A1 is equal to 0 actually. So note that if A1 is equal to 0, then what can we say? So if A1, suppose this was 0, now we have to find out. So these are n minus 1 bits remaining only. So first bit has been fixed to be 0. And in these n minus 1 bits, again, what we want is that there should be no consecutive ones, right? Because we need to have the property in this n-bit string itself that there should be no consecutive ones. And if first bit is 0, then to ensure that there are no consecutive ones, we just have to ensure that there are no consecutive ones in these n minus 1 bits. Because this is anyway 0, so this cannot cause any consecutive ones anyways. So that's why here we'll have something like a t of, sorry for this guy. So we'll have something like t of n minus 1 ways. Because if a1 is 0, then these n minus 1 bits can be set to anything such that they don't have any consecutive ones, which is just t of n minus 1. And then the case 2 will be when a1 is actually equal to 1. And if a1 is actually equal to 1, then to ensure that there are no consecutive ones, so if a1 is fixed at 1, then we'll have to fix a2 equal to 0 also, right? Because if a2 was also equal to 1, then we will have consecutive ones. A1, A2 will be consecutive ones. So that's why if we fix A1 to be 1, then we have to fix A2 is 0. So just writing this down. So in this case, A2 will need to be 0. A2 will need to be 0. Else we will have consecutive ones. Or maybe else A1 and A2 will be consecutive ones. So that's why A2 will need to be 0. And if A2 is 0, then we'll again have something like, so A1 is 1 and A2 is 0. And since this is 0, this won't affect any consecutive ones afterwards. So now we have these, if A1 and A2 are fixed to be 1 and 0 respectively, then we have these n minus 2 bits remaining. And these n minus 2 bits can be set to anything such that they do not have consecutive ones. So sort of we arrive at the case 1 itself, but just starting from A2. Earlier in case 1, A1 was 0, but now we have A2 as 0. So in this substring, if the first bit is 0, then the number of ways such that we do not obtain any consecutive ones can be obtained by just setting these n minus 2 bits in such a way that we do not obtain any consecutive. So that's why in this case, we'll obtain something like so we need to set these n minus 2 bits in such a way that they do not have any consecutive ones. And so this will give us something like t of n minus 2 bits. Yeah, yeah. So there were two cases. First case was when k1 is 0. Second case was when a1 is equal to 1. And we calculated in both the cases the number of ways. In first case, it was t of n minus 1. In second case, it was t of n minus 2. And since both cases are disjoint, like a1, in one case, a1 is 1, and in other case, a1 is 0. So both cases are disjoint. And note that they are exhaustive also, because this is a binary string, so A1 can only be 0 or 1 or not, and nothing else. So these are disjoint as well as exhaustive cases. So if we want to calculate the total number of ways for this n-bit string, it will just be sum of these two cases, because these two cases are disjoint as well as exhaustive. So just writing this down, since both cases are disjoint as well as exhaustive, and this is because why are they exhaustive? Because A1 can only be 0 or 1, either 0 or 1. And so we can sum up the number of ways for both the cases to find the total number of ways. So that is, so like it's easy to see like what I'm implying. So T of n will just be equal to the first case when A1 is 0, it will be T of n minus 1. And in second case, it will be T of n minus 2. And so like, and like this is like this recursive relation T of n is T of n minus 1 plus T of n minus 2. It's given in option A as well as option C, but the base cases in option A are T of 1 is 1 and T of 2 is 1. But that is incorrect. In option C, we have base cases that T of 1 is 2 and T of 2 is 3, which is the correct answer. So option C is actually correct. Hence, C is correct. So one more thing I wanted to add on here is like suppose this was more than one choice correct answer question, and let's say there was another option given to us. Like let's say there was another option given to us which was like T of n is equals to so what you can do actually is you can write T of n is equal to T of n minus 1 plus T of n minus 2, right? Maybe I should not write this option here, but just tell you guys. So if you write T of n equal to T of n minus 1 plus T of n minus 2, note that this is the not the only possible way to write the recursion, right? So I will just want to say that if you arrive at some recursion, then do check if the question is multiple choice correct, whether other recursions are also valid or not. And why am I claiming this? Because let's say we have this recursion as T of n is equal to T of n minus 1 plus T of n minus 2. Then we can also write it as, so suppose we know T of n is T of n minus 1 plus T of n minus 2. Then what can I do? I also know that if I put n minus 1 instead of n, then I can also write that T of n minus 1 is equal to T of n minus 2 plus T of n minus 3, right? I just replace n by n minus 1. And if I do something like this, then what happens is I can actually replace in this recursive relation the value of T of n minus 1 by this value. I know T of n is T of n minus 1 plus T of n minus 2. I also know that T of n minus 1 is T of n minus 2 plus T of n minus 3. So what do? I replace this T of n minus 1 by this value, T of n minus 2 plus T of n minus 3. And note that this is also a valid recursive relation, like something like this. T of n is equal to 2Tn minus 2 plus Tn minus 3. So this is also a valid recursive relation. And that's why I'm saying that be careful if the question is multiple choice correct to verify whether another recursive relation does not satisfy your answer. So if it is multiple choice correct, one can just give one option as this and another option as this. And suppose you arrive at this T of n minus 1 plus T of n minus 2 recursion and you just mark it, but you don't mark this option, then that will be incorrect, right? So just be careful. Like this is not a very uh, mathematically interesting thing. It's just like you can write one recursion in multiple ways, and so just be careful that to avoid any silly mistakes that you don't do mistakes like this. Then yeah, maybe I should just keep it as it was. So this was just a side remark. But here, like, this was just one option correct. And yeah, here we had t of n is equal to t of n minus 1 plus t of n minus 2. Okay, then let's moving on to the third question. Third question says that let A and be a sequence that satisfies the recursive relation A of n is equal to 20 a n minus 1 minus 25 a n minus 2. And we are given values of a naught and a1 as 4 and 14 respectively. And now we want to find out the values of a3 and a4. So note that what we are given here is we are given the recurrence relation, and we are also given the first two base cases of this recurrence relation. And now we want to find out like A3 and A4 here. So one method which might first come to mind is okay, so this has been discussed in the lectures, like how to solve a recursive relation, right? How to find out the explicit solution from a recursive relation, and that you do by replacing like an by x square, an minus 1 by x, and an minus 2 by a constant, and then solving the quadratic equation and finding its roots and something like that. So that kind of way is also valid. So one method which might come to mind in solving these kinds of questions would be to solve the what is the characteristic equation? Characteristic equation is the equation which is obtained by replacing an by x squared, an minus 1 by x, and an minus 2 by constant. So solve the characteristic equation of the recurrence, then find the constants using the base cases. So first you solve the characteristic equation and find the constants, like the constants are the coefficients of the like roots of the characteristic equation. Like all of this has been covered in the lecture, so I assume that you guys already know about this. So so the method one basically revolves around obtaining the general formula from this recursion. Like if we are given this recursion, then we want to find out the general formula for an. So one way, so what I'm claiming is like one method to solve this kind of question would be like obtaining the general formula for the values of n and then plugging n equal to 3 and n equal to 4. So we obtain the general formula for the recurrence relation, and then just plug n equals to 3 and n equals to 4 in the formula. So this is one method by which you can go about to solve the recurrent, like to find out the answers. Uh, you obtain using these conditions, you obtain the general formula for an, and then just put n equals to 3 and n equals to 4, which is a perfectly valid way. But I think, in my opinion, it's a longer method. You have to first solve the equation, then find out the roots and everything. So that is the only way to go about if you want to find out the general formula for an. But note that this question specifically does not ask us to solve general an. It just wants us to find out the values of a3 and a4. So the other method two would be, which I would advise you guys to prefer here for this question to solve the question faster, would be maybe just use this recursive relation to find out these A3s and A4s. And what do I mean by that? So suppose we are given this A0 and A1, then just iteratively we just calculate the values of using A0 and A1, we can calculate the value of A2. Then using A2 and A1, we can calculate the value of A3. And using A3 and A2, we can calculate the value of A4. So we can iteratively find out values of different AIs till we arrive at these A3s and A4s. So this might take longer if suppose we had to find out A100. Suppose we had to find out A100, then I believe solving the recurrence relation would be more advisable. But if you just have to find out the A3 and A4, then you have to do very few number of iterations. You just have to find out first A2, then A3, then A4. And so it would be faster. So this would be recommended here. And what do we do this? What do we do here? Just iteratively compute the values A2, A3, A4 from the given recurrence relation and the basis. So, like, yeah. So on a high level, this is the idea, and we can just do this also. And how do we do this? So suppose we have to find out what's the value of A2, then we can find A2 by just plugging n equals to 2 here. So if we have A2 equals to 20 A1 minus 25 A0. This will be 20 A1 minus, or maybe I should write the general formula first and then plug in. Yeah. Plugging n equals 2, we get A2 equals to 20 A1 minus 25 A. And this implies that A2 is nothing but 20 times A1, where A1 is 14. So 20 times 14 minus 25 times A0, which is 4. And from this, you can get the value like 20 times 14 will be something like 280, and 20 times 5 times 4 is 100. So 280 minus 100 will be 180. And now, since we have calculated the value of A2, using A2 and A1, we can calculate the value of A3 also. So plugging now n equals to 3, we'll get A3 is equals to 20 A2 minus 25 A1. And 20 times A2 will be nothing but 20 times A2 we obtained to be 180. So 20 times 180 minus 25 times A1, and A1 was 14. So 25 times 14. And what will this be equal to? So this will be 3600, and this will be something like 250 and 350. So 3600 minus 350, it will be something like 3250. Yeah. And then if we have this as 3250, now we can plug n equals to 4. Okay, I don't think I'll be able to calculate this directly. I'll need a calculator. But so we'll obtain A4 is equals to 20 times A3 minus 25 times A2. And now A4 will be like 20 times A3, and A3 was something like 3250. So 20 times 3250 minus 25 times A2, and A2 was 180. Okay, should I try to calculate this orally? Let's see. So 325 times 2 will be something like a 650. So this will be 650. So 6500. And so this will be 65,000 actually. So 65,000 minus 25 times 180. And this will be, so this can be 100 and this will be 45. So this will be 65,000 minus 4,500. And that will give us something like 60,500 would be the answer. Yeah. So this will be 60,500. And now, so this is the values which we get. So we had to find out the values of A3 and A4. So using just 2 or 3 simple calculations, we were able to do, and we did not need to solve any equations or anything. That's why I prefer this formula when we just have to find out smaller values. And so hence we get A3 is equals to 3250, and A4 is equals to 60,500. So this is the final answer. Maybe I'll just put this. Yeah. Okay, then let's move on to the fourth question. So fourth question says that given the sequence 0, 1, 1, 2, 3, 5, 8, 13, what is the 23rd term in this sequence? So one thing which you can easily see here is this is nothing but the Fibonacci sequence, right? So this is nothing but the Fibonacci sequence. Like this has been covered in the lectures also. So the sum of like the nth term is just the sum of n minus 1 and n minus 2 terms. So like 8 is just the term before plus the term before the previous term. So like the last two terms will sum up to give us the next term. So 3 plus 5 gives 8. Similarly, 5 plus 8 gives 13. 13 plus 8 gives 21. So next term will be 21 and so on. So this is the Fibonacci sequence which is given to us. So the given sequence is the Fibonacci sequence. And what we need to do is, so we just need to find the 23rd term of the Fibonacci sequence. So this can be done like again, this can. So this is again like similar to this question. We had an. So now we have an equals to an minus 1 plus an minus 2. And we have to calculate a23. So there are two methods for the characteristic equation and obtain the general formula. So we already know the general formula for Fibonacci, but it's a bit complicated. Like it involves square roots and everything. So still, I would advise the method 2 to calculate the 23rd term. Like again, just do it iteratively. So this can again be done. This can be done either using the. So this is the iterative method which I'm talking about, or this is the characteristic solving the characteristic equation method. But I believe this iterative method is the one which usually helps us more while calculating explicit values for a recursive sequence. So yeah, can be either done using the iterative method or using the general formula Fibonacci sequence, right? And okay, so for this question, like you can do this yourself, like finding out the 23rd. But the answer, I'll just give it to you guys that the answer which should come out should be something like 28567. So I already had the answer written down for this. So yeah, this is the 23rd term in this sequence, the term 28567. And yeah, do it yourself. So this question was just to remind everyone about what is the Fibonacci sequence. So yeah. Now maybe we can move on to the fifth question. So fifth question says that Paras is reading a novel that consists of n pages. While he reads the book, his dad calls him for some work. Being in a hurry, he forgets to put the bookmark on the page he was reading. So he remembers the page number. How much efforts will Paras require to get back to the page he last visited? Ah, okay, guys, sorry, I'll have to mute myself for 2-3 minutes. There's a urgent call coming. I'll just come right back. Sorry for that, guys, again. So this question states that effectively you remember. So suppose you remember the page number which you have to open in a book, but you don't have a bookmark, so it's not possible to direct. Suppose there is a book and you have to open the 100th page of the book, so you can't just open directly the 100th page because like no one is that precise usually, right? But what we are precise usually is so that's why we'll take, like, you can't open it in the first try, you can't open the 100th page in the first try. But what you can do is maybe open some pages, and in some tries you will go to the 100th page. So while we are not usually good at opening the exact page, like you can't always open the 100th page exactly, but you are usually able to open approximately the half of the book. So suppose book was of length 500, there are 500 pages in the book, then one is usually able to open the page around 250th, open the page close to 250th page of the book, right? Like you can uh, approximately open the half of the book, the middle of the book, okay. The middle page of the book you can approximately open. You can't open exactly the page number which you want, but usually we are good at opening the middle page of the book. So the idea here is similar to binary search, which has already been discussed in the lectures. So even though you don't remember the exact page number, but you can go to that page number quite fast, like in very few attempts, by following a procedure similar to binary search. So what you can do is you open the middle page of the book and you see whether the page number which you want is greater than the page number which you are currently at, or is less than, and then you can recurse on the side where you want to go. And note that, like, you can't open exactly the middle page of the book either, but you can approximately open. So approximately at each step, the number of pages which you want to search over gets halved. It does not exactly get halved, but it approximately gets halved. And that is good enough for us. Like, because after approximately log n trials, we will be able to go to the page which we want. So because binary search takes log n steps. So just writing it down here. So log n steps will be needed. Okay, yeah. Yeah. So log n steps. So not exactly, you can't always guarantee that you will be able to do it in log n steps, but approximately log n steps will be needed, like order of log n, let's say order of log n steps, where order just denotes like the complexity. So order of log n steps will be needed. And why is this? Uh, this is because this can be. And note that in a binary search also, you can't do, like, in a search problem also, you can't do usually better than login, right? Binary search is the most efficient algorithm and it requires login. Wait, login steps at least. So this is actually optimal. Like, you know a procedure which approximately uses login steps, and you also know that less than login steps is not possible. So this is actually optimal. Yeah, this is a side note which I wanted to give, but maybe we can just write down the solution as well. So this can be thought of as a binary search problem, as we can always open the approximately middle page of a book. And approximately middle, I mean, suppose if a book has 200 pages, you can't open exactly 100 page, but you will, if you go to approximately middle, you will be usually able to, like, open a page which is like between the ranges 90 to 110. So something like that. That's why approximately middle page, I'm saying. So we can always open the approximately middle page of the book. So what do we do is, so we keep having the number of pages at every step, which is similar to which is similar to binary search. So this is the high level idea, and that's why we need like order log n steps, because binary search also takes the order log n steps. So yeah, note that this procedure is optimal because searching always takes at least log n order log n steps. Maybe it's like this. Yeah. This procedure is optimal because binary search is optimal. And why is binary search optimal? Because searching takes at least log n steps. And a high level intuition of why do we need log n steps is because so there are n numbers and each number is represented, let's say, by a binary notation in a binary notation. So there are log n bits for one number. And at one step, we can only know only one of the bits of the number. And we, for explicitly determining a number, we require to identify log n bits. And that's why this is the information theoretic bound, that we need to identify log n bits. And so log n bits cannot be identified in less than log n time, like in less than log n steps. Like, this is not practical. Like this just means that for storing log n independent pieces of information, you will need log n space. And like this is true. So that's why this is somewhat optimal. This is a very high level argument, but more or less, like, I won't try to make it formal, but this is the high level idea, that log n steps are needed and lower bound of log n is also there. And now, just a interesting question for everyone, like, okay, not like, let's just keep it here. So how will the answer change? So here what we had is like Paras forgot to put the bookmark on the page he was reading, right? So suppose for Paras did not forget, like, how will the answer change if Paras had indeed put a bookmark? If Paras had put a bookmark on the required page. So in this case, this is easy to see. Like, if Paras had indeed put a bookmark on the required page, then we can directly obtain the required page in one step. And this is because Paras can directly open the bookmark page. So yeah. So like, this is just this is not too difficult of a question. I just want to make it explicit. Like, so the complexity of putting a bookmark. So note that whenever you forget to put a bookmark, it means that instead of one step, you will be requiring approximately log n steps in the future. So always remember to put a bookmark, guys. Yeah. Now let's move on to the sixth question. So sixth question says that which of the following is the correct recurrence relation for climbing 20 stairs? Climbing stairs means walking on stairs, covering either one or two stairs in one step. So like, this problem has already been discussed in the lectures. Also, we have to climb n stairs and we can only climb one or two stairs in one step. And here, like, these ANs denote actually the number of ways. So AN denotes the number of ways to climb n stairs actually. So number of ways of climbing n stairs. And this is how we discuss in the lectures, that reconciliation for this is nothing but A of n is equals to A of n minus 1 plus A of n minus 2. And like this, why is this true? This is true because this has already discussed in the lectures, right? So what we have is like, suppose we have to find out 20 spheres, correct expression for 20 spheres, just put n equals to 20 here, and we get putting n equals 20, we get A of 20, so n minus 2 will be now 18, n minus 1 will be 19, and this will be 20. So A of 20 is nothing but A of 19 plus A of 18, and this is like option D. So option D is correct here. And option B is correct. So not too difficult. It's just a very straightforward question. Okay. Now we move on to the seventh question. So seventh question says that what can we say about the following functions? So we are given four functions. F1 of n is 40n cube, F2 of n is 50n square, F3 of n is 23n square plus 20n, and F4n is 18n cube plus 5n square plus 9n. And there are multiple statements given to us, and like it is more than one choice, correct? Like there can be more than one statement, correct? Also, so we have to find out which of the following statements are true. So let's go statement by statement. So maybe let's go by option A. So option A says that F3 of n is an order n function. So F3 of n is this 23n square plus 20n. And the statement says that it's an order n function. So note that this is incorrect because like this has the highest degree of n in this F3 of n is actually n square and not n. And note that n square has a higher complexity than n. So this is not an order n function, but rather an order n square function. So that's why option A is actually incorrect. Incorrect, and this is because like n square is greater than n. And note that this greater than I do not mean like explicitly greater than as in inequalities. What I mean is n square has a higher complexity than, like we discussed in the first question. So this similarly, this greater than less than, I mean here also like n square has a higher complexity than n. That's why option A is incorrect. Option B states that F2 of n grows faster than F1 of n. So again, grows faster means like has a higher complexity than. So this statement claims that F2 of n has a higher complexity than F1 of n. So let's see, F2 of n is 50n square. So, and F1 of n is like 40n cube. So ignoring the constants, this is n square and this is n cube. But note that actually n cube has a higher complexity than n square. So actually F2 of n grows slower than F1 of n. So this is incorrect. Again, incorrect, as n cube is greater than n square. I hope this makes sense. Then moving on to option C. In option C, we have F4 of n is an order n cube function. So F4 of n is 18n cube plus 5n square plus 9n. So actually, like here, the highest power of n is actually n cube. So this is indeed an order n cube function. So this is correct. So this is correct because F4 of n has highest power as n cube. So, yeah. Then moving on to option D. In option D, we have F2 of n and F3 of n grows lower than F1 of n. So F2 of n is 50n square, F1 of n is 40n cube. So this is true that ignore the constant that n cube is greater than n square. So f2 of n grows slower than f1 of n. Similarly, f3 of n is also like the highest power of n is n square here. So this also grows slower than n cube. This statement is also correct. So correct as n square is actually less than n cube. So yeah. So what we get is statements, options C and Hence option C and D correct. Okay, then we can move on to the eighth question. So eighth question says that what is the solution of the recurrence relation A of n is equals to 3an minus 1 plus 10an minus 2. Right. So this is just sort of a like solving the recurrence relations given the base cases has already been discussed in the lectures, but just for practice, we'll be discussing one such question explicitly also. So how do we do this? So the high level idea to solve these sorts of reconciliation is first obtain the characteristic equation and then solve the characteristic equation to obtain the roots of the equation and then find out the constants associated with those roots. Okay. So the high level plan for us will be first write down the characteristic equation for this recurrence and then solving the characteristic equation. And how do we obtain the characteristic equation? So this has already been discussed in the lectures. So just replace the n by x square, an by x square, an minus 1 by x, and an minus 2 by 1, and we'll have the characteristic equation. To obtain the characteristic equation of the above recurrence, just replace a of n by x square, a of n minus 1 by x, and a of n minus 2 by 1. And if we do this, we obtain the characteristic equation as. So what will the characteristic equation be? The characteristic equation is, so an will be x squared, so x squared is equals to 3 times x plus, so this is x squared is 3 times x plus 10. And from this, solving this equation, we'll obtain the roots. And what will be the roots of this quadratic equation? So x squared is 3x plus 10. So this can be written as x minus 5 times x plus 2 is 10. So this will be like x equals to 5 comma minus 2 will be the roots. Yeah. Okay, maybe I should move this whole question to the next page. Yeah. And now, if we have this, then we know that this has already been discussed in the lecture. So an will be of the form. So after obtaining the roots, so an is of the form of some multiples of these roots. So a linear combination of these roots. So an is equal to c1 times 5 raised to the power n plus c2 times minus 2 raised to the power n. So this is what an is actually equal to. But we don't know what these values of c1 and c2s are. So we'll obtain the c1 and c2 using these equations, like using these base cases. So putting n equals to 0, we can obtain that a naught equal to c1 times 5 raised to the power 0 plus c2 times minus 2 raised to the power 0. And similarly, we can obtain putting n equals to 1 also another. So putting n equals 0, what we get is a naught is equal to like 3 times. Okay, so A naught is equals to C1 times 5 raised to the power 0 plus C2 times minus 2 raised to the power 0. And A naught, we are given that A naught is actually equal to 1. So this equation will just reduce to 1 equals to C1 times 5 raised to the power 0 will be C1 plus C2 times minus 2 raised to the power 0. This will also be 1. So this will be C1 plus C2. So this is the first equation which we obtained. And now the second equation will be obtained by putting n equals to 1. Putting n equals to 1, what do we get? We get that A1 is equals to, again, maybe I should copy this and put it equals to 1. So A1 will be nothing but C1 5 raised to the power 1 plus C2 minus 2 raised to the power 1. And from this, we get that A1 will be nothing but 2. So 2 equals to 5C1 minus 2C2. Right? So we have now two equations and we have two variables C1 and C2. So solving the above equations, what we'll get. So we can solve the above equation. Solving the above equation. So we'll get values of C1 and C2. And what will be the values? Maybe we can calculate it orally. C1 equals to something and C2 equals to something. What will be the value of C1 C2? So let's just see. 1 is equals to C1 plus C2 and minus 2 equal to 5 C1 minus 2 C2. So we multiply this equation by 2. So we'll get 2 equals to 2C1 plus 2C2 and then add these two equations. Then we'll obtain actually 4 equals to 7C1 and these 2C2 minus 2C2 will cancel. So we'll obtain 4 equals to 7C1 and we'll obtain C1 as something like a 4 by 7 of that. And C2 will be, yeah. And what will the value of C2? If we put C1 equals to 4 by 7 here, we'll obtain C2 equals to 3 by 7. 3 by 7. So these are the values of C1 and C2. C1 is 4 by 7 and C2 is 3 by 7. And from this, putting values of C1 and C2 in the formula for AN. So in the formula for AN, if we when we put the value of C1 and C2, we get that AN is actually equal to okay. C1 is nothing but 3 by 7. So AN is okay, A1 is 4 by 7. So 4 by 7 times 5 raised to the power n plus C2 is 3 by 7. So this is 3 by 7 times minus 2 raised to the power n. Hence, so, yeah. So not too difficult, like just initially found out so on a high level, we first wrote the characteristic equation, which is simple. Then we found out the roots of the equation. Then we wrote AN as like roots raised to the power n and their linear combinations. And we found out these coefficients of the linear combinations using the base cases. And that's how we obtained the value of AN. Okay. So then this brings us to the last question of the day, the ninth question, which I prepared. So this is again not too difficult of a question, but yeah, it just shows recursion in a different manner. Like, So till now we have discussed recursions related to these recursive formulas as numbers and stuff like an equals 3 of an minus 1 plus n of an minus 2. So we are given some numbers, and from those numbers we obtain some recursive formula to obtain other numbers. But here in this question, we actually do not have numbers, but rather we have a set, and this grows, and this set grows actually recursively. So the question is quite simple, but I just wanted you guys to understand the power of recursion. Like recursion is not just limited to numbers, it can also be applied to sets and so on. So let's suppose that let S be the subset of the set of ordered pairs of integers defined recursively. So we define this set S recursively. Okay, so the S is a subset of the set of ordered pairs of integers. So S is actually S consists of some ordered pairs of integers, right? And what's the definition of S? What elements are contained in S? So first of all, we are given the base case, like here we are given values of A not A1. Similarly, here we are given the base case that 0, 0 belongs to S. Okay, so the base case is that we have 0, 0 should be in S. And then the inductive step, or let's say the recursive step, is that if A comma B belongs to S, then A plus 2 comma B plus 3 and A plus 3 comma B plus 2 also belong to S. So this is the recursive. So you can think of this as a recursive step. Like suppose if 0, 0 was the first element of the set S, then the next elements can be defined by A plus 2 comma B plus 3, like 2 comma 3 and 3 comma 2. Similarly, in the other step, we'll obtain other values. Right. So this set S is also defined recursively here. Like recursion is not just limited to numbers, but can also be applied to sets. And so now the question is not too difficult, I believe, but let's answer this. So the first part says that list the elements of S produced by the first 5 applications of the recursive definitions. So let's go to the first part. So list the elements of S produced by the first 5 applications of the recursive definition. So first of all, we know that 0, 0 belongs to S, right? So we know that initially we know that 0, 0 belongs to S. And now we can keep on applying this recursive definition to obtain other elements, right? So first application, so uh, after first application, okay, so uh, after first applications, what are the elements which we'll get? So we know that while applying the first application, while applying this recursive formula first, we just know that 0, 0 belongs to S, right? We don't know anything else about the set S. But if we know that 0, 0, if A and B are equal to 0, so we know that if 0, 0 belongs to S, then these values also belong to S, and A and B are 0. Uh, so we also know that. So putting A equals to 0 and B equal to 0, we get that 2, 3 and 3, 2 belong to S. So maybe I should just put this here. A and B are 0, so 2, 3 belongs to S, and 3, 2 belongs to S. So now we know more elements of S now. So we initially knew only 0, 0 was a member of S. After first application, we come to know that 2, 3 and 3, 2 also are part of S. And now in the second application, okay, so now maybe I should just copy this. So after second application, what we know is, so we know that, so 0, 0 we already handled, we already obtained this 2, 3 and 3, 2, but now these are new elements, right? So in the second iteration, we can first apply this definition for this 2, 3 element. So if 2, 3 belongs to S, then 4, 6 also belongs to S, and 5, 5 also belongs to S. So maybe we can write 4. So like if A equals to 2 and B equals to 3, we'll obtain something like 4, 6 belongs to S. Similarly, we'll obtain something like so 2, so we'll also obtain 5, 5 belong to S. I should just copy this. This will be 5 comma 5 also, because if a equal to 2 and b equal to 3, then this will give us 5 comma 5. Similarly, we also knew that 3 comma 2 belongs to S initially, right? Before applying the second application. So if 3 comma 2 belongs to S, then a equals to 3 and b equals to 2. So putting a equals to 3 and b equal to 2, we'll get 5 comma 5 here, which we already obtained. But second thing we'll obtain is like 3 plus 3, which is 6, and this is 4. So we'll obtain 6 comma 4 also belongs to S. So these are the 3 new elements which we obtain on applying the second application. Okay, let's not just do 5, but let's just do 5 will take. So after second application, we know these are the 3 new elements which we obtain. 4 comma 6, 5 comma 5, and 6 comma 4. And now we move to the third application. So after third application, what will we first of all, so now, okay, so in the second step, we know that these 2 elements are also part of S. And now in third, in the second, after second application, we also came to know that these elements are also part of S. And now we'll try to uh, find other elements of S also. So now first of all, we know 4 comma 6 belongs to S. So if 4 comma 6 belongs to S, then A equals to 4 and B equals to 6. Then A plus 2 comma B plus 3 will be just 6 comma 9. So we now know that 6 comma 9 also belongs to S. Similarly, A plus 3 comma B plus 2 will give us 7 comma 8. So 7 comma 8 also belongs to S. So 6 comma 9 and 7 comma 8 we obtain using this 4 comma 6. And now we also know that 5 comma 5 belongs to S. So A equals 5, B equals to 5. So A plus 2 comma B plus 3 will give us something like 7 comma 8, which we already have here. So we don't need 7 comma 8 here. Yeah, maybe I should delete this. Yeah. So we had this 5 comma 5, right? And from this 5 comma 5, we replace it by A plus 2 comma B plus 3 if A is 5 and B is 5. So we'll obtain this as 7 comma 8. But 7 comma 8 we already know belongs to S. So we don't need to again write it. But the other thing, A plus 3 comma B plus 2 will give us something like 8 comma 7, which we did not have before. So 8 comma 7 we also come to know belongs to S. Similarly, now we go on to this 6 comma 4. So 6 comma 4, if A is 6 and B is 4, then we know that A plus 2 comma B plus 3 will also be part of S. So A plus 2 will be 8 and this will be 7. So 8 comma 7 is a part of S, which we already know though. So we don't need to write it again. But this A plus 3 comma B plus 2 will give us something like a 9 comma 6, which we did not know earlier. So 9 comma 6 also belongs to S. So after third application, we get these 4 new elements. And similarly, like this set S can be defined recursively, and you can apply further applications to find out other elements. But after the first 3 applications, these are the elements which we obtain, like 0 comma 0, 2 comma 3, 3 comma 2, and so on. So maybe just should write the answer here. So hence the elements of S obtained after first 3 applications of the recursive definition are. So what are the elements obtained? So we obtained the element 0 comma 0. Then we had this 2 comma 3 and 3 comma 2, 2 comma 3, 3 comma 2. Then we had this 4 comma 6, 5 comma 5, and 6 comma 4. So 4 comma 6. Maybe I should write it. This will be faster. 5 comma 5, then 6 comma 4. Then we had 6 comma 9, 7 comma 8. Yeah. So 6 comma 9, 7 comma 8, 8 comma 7, and 9 comma 6. So these are the elements obtained of S after first 3 applications. So note that in this recursive definition, the advantage is that instead of listing out uh, elements of S by some other property, we just need to list out one element, and then after recursive definition, we were able to expand this set. That even after just three applications, the elements of the set are the elements which we have identified, which are part of this set are like we are identified how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So even after just first three applications, we were able to identify 10 elements of the set S. And this will go on as we further apply this recursive definition in further iterations. Yeah. So yeah, like this question is not too difficult, like quite straightforward, but uh, the main message which I want to convey using this question is that you can use recursion to define sets also. And now moving on to the B part. So B part is not too difficult. Like this is just a inductive argument, I would say. Like 5. So suppose 5 divides A plus B when A comma B belongs to S. So we have to claim whether this statement is true or false. Like if A comma B is a member of S, then 5 will divide A plus B. Is this statement true or false? So actually, first let's just see the elements of S which we have obtained using this, whether we can verify whether, like at least, does this statement hold for the elements which we have identified? If we see even one element for which 5 does not divide A plus B, then we are already sure that this statement will be false. But let's just see. So the elements which we obtained already are 0, 0. So 0 plus 0 is 0. So 5 divides 0. Similarly, 5 divides 5. Here sum is also 5. Here sum is 10. So for all these, the sum is 10. So these are also divisible by 5. Here the sum is 15. So these are also divisible by 5. So at least the elements which we have obtained already are all divisible by 5. So maybe this claim is true. And actually, yes, this claim is actually true. And you can, but you can't just say like, but if something is true, you have to prove that it is true, right? Otherwise, it's just a vacuous statement. Like, why will someone agree that this is true? For proving that a statement is true, you have to show this for all possible cases. This is true. We just showed that for after the first three iterations, this statement is true. We just verified this, but we want to actually prove that uh, even after any n number of iterations, this statement will hold true. Not just after three iterations, but even after n iterations, this statement will hold. And again, this can be argued using induction, like true. And like, how do we prove that this is true? So again, like for proving this statement was false, we just need to obtain a counterexample. But for it proving it to be true, we need to actually write down the whole proof. And how can we prove this? Can be proved using actually induction. And like, yeah, can be proved using induction. And I would say like, yeah, this can be somewhat of a homework. Like this is not too difficult. Like you should try this yourself. Like how can we prove this using? How can we prove this claim using induction that 5 divides A plus B when A comma B belongs to us? I suppose we have already come a lot far in this course that you guys should be able to do these kinds of proof yourself. So the high level idea I believe is very clear. Like you can just see like inductive claim can be somewhat something like we know that initially the like the initial element 0, 0 belongs to S. So this is the base case. An inductive case can be suppose after n iterations, all the elements of S have this property that 5 divides A plus B. Then even in the n plus 1th iteration, you can prove that this property is preserved. And the high level idea of why this property is preserved is suppose if A plus B belongs to S in the nth iteration, then we know that 5 divides A plus B. Then in the n plus 1th iteration, you will arrive at these terms A plus 2, B plus 3. And the sum here would be A plus B plus 5. And since A plus B was already divisible by 5, A plus B plus 5 will also be divisible by 5. And so after the n plus 1th iteration also, the elements obtained will be still divisible by 5. The sum of the elements of the pairs will be divisible by 5 for all pairs. And this is sort of the inductive argument by which you can prove this. So more or less, I've already given away the whole proof, but just to explicitly write it down yourself, I'll recommend you guys to try this yourself. But the high level idea is this only, that you can apply induction on the number of applications of the recursive step. Yeah. So, okay, then I guess this was it for today. Like, this was the last question which I had for discussing today. And yeah, we are done like a bit earlier than time, but since I believe like we finished early today because no one joined the session in person today, and that's why there were no questions. So usually there are questions, and that's why uh, it takes a bit more time, but it got a bit early to it got over a bit early today. And yeah, since no one is present, I guess we can just close the session since no one is around. Yeah, these are the questions which I had in mind. So once again, just once again, thanks to everyone who's watching on YouTube for watching this session, and hopefully I'll see you guys in person next time. In the same timings, Monday 6 to 8 p.m. And next time will be the last session, the session 12 for us. So yeah, we'll be covering the contents of the last week in that session. So okay then, until next time, goodbye guys. I'll be closing the session and yeah, bye bye.